All right, so let's move to chapter 2 of this book. We'll fill in any gaps on prerequisites, maybe even this lecture actually. But chapter 2 of this book is dedicated to the subject of identifying the classical groups. Now, ultimately, this will tie into the subject of our Lie groups, of course, but we're interested in a collection of specific groups that we want to understand the nature of, and that's the goal of this chapter. There's a lot to it, actually. I've listed some pictures, or I've written down what these groups look like, so you can remember that you've seen these before in your reading, I'm sure. The general linear group of n dimensions in real numbers, in complex numbers, and in quaternions. I put H here because one of our viewers pointed out that H is the sort of the standard for the set of quaternions. Gilmore uses Q. He uses actually a boldface Q. I'm using the sort of blackboard stylish Q or Gothic Q or something. We're going to stick with Q for this because that's what Gilmore does. But it is true that H is more the standard for the set of quaternions. Also, another viewer noted, very importantly, I think, that I called these three sets fields, and quaternions are not commutative. And clearly, the way I was expressing it, fields do not require commutivity. However, the more standard definition of fields does in fact require commutivity. In other words, the word field in mathematics implies a commutative division ring, right? So quaternions don't fit that definition. However, Gilmore's use of the word fields does not require commutivity. Commutivity is an option, and if a field commutes, it's called a commutative field in his language. So he would call the quaternions, he would call real and complex numbers commutative fields. There is a concept out there of skew fields, which are non-commutative fields. However, the standard definition of fields that you find in most of the most modern stuff actually does have as one of the axioms that a field must be commutative. Q1, Q2 must equal Q2, Q1. So there's been a little bit of a shift somewhere back in time, or a split between the way the word field is defined in mathematics, but the viewer is actually more definitely right in that the most common use, if you study the fields out there now, you're almost certainly going to get a definition that includes commutivity. So keep that in mind, although Gilmore does not. So this is sort of important because the question is, we use words to define things that, to bunch things up that have properties that are similar enough that we can study them all together. So presumably, the study of fields, there's something important about commutivity that makes fields useful in some viewpoint, but then the idea of studying just a division ring, right? A division ring, which is what a field is. A field is a division ring, but if it's a non-commutative division ring, that's something else. So regardless, these three things here, what's important for our purposes in the modern language is we're dealing with non-commutative division rings. Gilmore calls them fields. Whatever. Okay, so we'll move on. Oh, but I do want to thank the viewer for pointing that out. I didn't recognize it. And what's ironic is I did a course in algebraic structures in the What is a Tensor series, and I defined fields there, and I used the modern definition where it was commutative. So I didn't even notice that I had slipped into a self-inconsistency. So thank you. But anyway, just to point out the rest of these groups, we have orthogonal groups, and it's interesting. You have three parameters that you need to know what field you're dealing with, and you need to know these two numbers, plus and minus, a positive number of dimensions and a negative number of dimensions. That's kind of interesting. That's meant to be a semicolon. You can do this in the reals, the complex, or the quaternions. There's unitary groups. Likewise, you need two numbers for the unitary groups. Now, you'll say, well, wait a minute, but I've seen unitary, UN. I've seen SUN, right? Oh, I didn't even put those in there. There's also SU and SO, right? There's special versions of all of these. And we'll discuss all those in time. These are the symplectic groups, which, by the way, have to have even dimensions, the way we've written them here. Oh, but not the quaternions. The quaternions, you can actually do this without even dimensions. Okay, so ultimately our goal in the next few lessons is to understand what all of these groups mean and why they're distinct, and get a complete picture of the classical groups. And that'll become our foundation to understanding Lie groups. So to understand these classical groups, we really have to understand the idea of a change of basis, strangely enough, which is really interesting because this goes all the way back to our what is a tensor kind of material. We're actually going to be reviewing some of that. So we want to consider some of the elementary vector spaces that could exist. Rn, Cn, and Qn. Now I put it in the superscript. I don't know if Gilmore does that. Actually, Gilmore likes to write it this way: Rn, Cn, and Qn. Now Rn is supposed to be an n-dimensional vector space over the reals. An n-dimensional vector space over the reals. So how would we construct that? Because you really have to understand these things solid because we use them forever, right? This will be for the rest of the material. So we know that for an n-dimensional vector space, we need to have n basis vectors. So I guess if I start at 0, I'll end up with n minus 1 here, right? Now that is true for, this is the collection of basis vectors. So I'm going to, well, I'll just put them off like that. That is true for all of these. I just need to have n basis vectors, all for whether it's the complex or the quaternions, E0, E1, ... all the way to En minus 1. They all have n basis vectors. Just because I've drawn them with the same letter, I'm attributing these basis vectors to the n-dimensional real vector space, the n-dimensional complex, and the n-dimensional quaternionic. The R is really kind of telling us that that's the bin of scalars we're dealing with. So we're dealing with the real numbers here, the complex numbers here, and the quaternions here as there are scalars. So it's interesting because now I'm talking about, it's pretty easy to understand in terms of real numbers because I could create an obvious realization of this vector space. It's a vector space, right? And I could create the realization 1, 0, 0, 0. Let's do it for 4 dimensions. Let's say I was creating R4. Any vector in R4 is some real number times this vector, can be represented by another real number times this vector, plus another real number times this vector, plus another real number times, obviously, this vector, right? This is very standard stuff, but it's a big deal because what I've done is I've now created a realization of this very abstract idea of 4 basis vectors. And that realization is this column matrix. That's the realization I've chosen. And any element of R4 can now be understood as simply a column vector, A, B, C, D, like that. But that is 4-dimensional. There's no doubt that that's 4-dimensional. So if we did the same thing with the complex numbers, everything is identical except this now becomes C4, and A, B, C, and D are now elements of the complex numbers. And this final thing here, this final result, are, let's see, complex numbers. I guess, well, the final result could ultimately be broken down into A0 plus IA1, B0 plus IB1, C0 plus IC1, and D0 plus ID1, right? So it's 4-dimensional. It's still a 4-dimensional vector space in the sense that it has 4 basis vectors, right? But the bin of scalars is now the complex numbers. So it kind of looks like, well, wait a minute. You've got 4 numbers here and 4 numbers here. I need 8 numbers to specify this. And that's true, right? That's true. I can understand the four-dimensional complex C4, I can understand that in terms of R8, right? So if I was going to try to write this vector space equivalently in terms of a real vector space, I would need 8 dimensions in the real vector space to accommodate the 4 dimensions in the complex vector space. And a similar problem happens for the quaternions, where all of a sudden now we boost it up to 16. So I would need R16 to do Q4, right? But the point is this dimensionality here is not really the raw amount of single digits that you need to produce the object in the vector space. This has to do with the number of basis vectors, And it is definitely true that Cn, the n-dimensional complex vector space here is equivalent more or less to R8, depending on if you construct it correctly. It's equivalent to an R8, but it's different, right? It's different. It comes from the bin of scalars is the complex numbers, and the quaternions are similarly situated. The point being, though, that we're going to be talking about changes of basis of these three vector spaces. So how would a change of basis be understood? Well, we begin by understanding that, going back to Rn, if any vector v in Rn can be written as a e0 plus b e1 plus c e2 plus d e3, right, where these guys are real numbers. We now know that in particular, I can always write, if I'm going to switch basis, and I'm going to now create a basis f0, f1, f2, and f3. These guys are vectors in the vector space, so I know that I can write f0 as some collection of, say, ABCD. I'll go f e0 plus g e1 plus h e2 plus I don't want to use K, plus L, E, 3, right? I can definitely write any of the new basis vectors in terms of the old basis vectors. But what's important is that these guys here are still real numbers. F, G, H, and L are real numbers. And I can create a matrix like this for each value of F. Actually, I shouldn't use F there, right? Because F is sort of the name of the basis vector. So I'll call that M. So the way we've always done this, and the way we've always written this down from the what is a tensor series, and I'll do this exactly the way Gilmore does it, is we want to say that the new basis, which we call the prime basis, the jth new basis vector, is some matrix of real numbers, J, I, summed over the old basis vectors. And this is a matrix of real numbers, right? That's a matrix of real numbers. And it's important that the matrix is non-singular, right? So this is invertible. It's an invertible matrix of real numbers. You should be able to go between both of these basis vectors by using the inverse matrix. In other words, EI would be A inverse J I E prime I, like that. Something like that. Is that right? No, E J, the old basis is the inverse of matrix element times the new basis. This should be somewhat old hat for you, but the point is that this is a matrix of real numbers, as long as we're dealing with vectors in Rn. But as soon as I deal with vectors in Cn, the same rule applies. The same rule applies exactly. There's no difference except that we're now dealing with matrix of complex numbers, because E prime 1 is now going to be some complex number times E0 plus some other complex number times E1 plus some other complex number, ZW. Usually complex numbers have these ZWs in it. Sometimes S is a complex number. You see that a lot. And then plus, I'll do Q at the risk of confusing with quaternions. So the new basis vector for a complex vector space, right, that's this guy, is going to be a complex number times the 4 basis vectors. So now this matrix has to be a matrix of complex numbers, and likewise for quaternions, right? And again, they have to be invertible matrices. They can't be singular, right? And those guys, the matrices that can affect these basis changes in Rn, Cn, and Qn, those matrices are called the general linear group in n dimensions of R, the general linear group in n dimensions C, and the general linear group in n dimensions Q. All right, now why is it a group? It's a group under what operation? If I said it's a group, I need to tell you the group operation. So let's cover that. All right, so the general linear group is all these invertible n by n matrices with entries from the field. And I'm getting, like I said, I'm getting very self-conscious about using the word field now. It actually turns out that I went even to a different book that I used to use, and that book also follows the standard that R and C are fields because they are commutative, and then it says that and it uses H for the quaternions. They're a non-commutative field, it calls it, but it makes it very clear it's not a field. It's a non-commutative field, which really means it's a non-commutative division ring. So, but Gilmore just does it, so I'm going to stick with it just for that reason alone. I probably should stop. All right, you know what? I'm going to stop. I'm not going to do it. So the general linear group in n dimensions for either R, Q, or C, complex, real, or quaternions, which I'll just sort of arbitrarily write as F for now, is the set of all invertible n by n matrices with entries from either R, C, or the quaternions. And that forms a group under the operation of matrix multiplication. Therefore, if I take one element out of that set, and it's a matrix, an invertible matrix, and then I take another matrix and I do a matrix multiplication, I get a third matrix which is in the set, and it's also going to be invertible, and therefore it is closed. I also know by definition it's invertible, and I know that a unit exists, again, because they're invertible. A unit must exist, otherwise inversion doesn't make much sense. And we know matrix multiplication is associative. So the GLNF is a group. So all three of these guys are going to be groups under the operation of matrix multiplication. So now the way you see this written a lot is the group itself is a set, right? And I write the set with this name, and what I'm going to actually say is this operation takes 2 elements from the set and returns a third. And the way the mathematicians always do this is they form the Cartesian product. So they'll say GLNF, Cartesian product GLNF, that's a set, right? And this is the set of all ordered pairs, where the first pair is an element of GLNF, and the second pair is an element of the linear group NF. And you have the set of all possible ordered pairs. And a mapping from that set into GLNF, that is the group operation. It takes 2 elements from GLNF, and formally what you're doing is you're dipping into the set of all ordered pairs, and then each of those ordered pairs is mapped to a single matrix from this set of the general linear group. So this Cartesian product, remember, it shows up there to help us define these mappings. And in a very, very formal way, you are really talking about mapping from this Cartesian product set into the original set. And that's this that's this mapping that we're talking about here, the group operation mapping. So that's the general linear group as a group. What's really important to understand is we got to remember where this came from. This came from from all possible ways of changing a basis in Rn, Cn, or Qn, right? That's kind of where we actually started. We started with the study of these things, 3 different vector spaces that are that have in 4 dimensions. We studied 4 dimensions, but it could have n dimensions. And we asked about changing the basis vectors, changing the coordinate system by which these vectors are measured in, or changing the basis. And so we're talking about matrices because matrices affect those changes, right? That's what we learned here. But these guys are relevant to these guys in a way that's altogether different than the group operation. That's why I want to emphasize this. There's also clearly another map out there that goes from GLNF cross FN, and it goes back to FN. You know, I probably shouldn't have the script either thing. I'll just make it like that. So, in other words, the members of this group are basis transformations. Therefore, they can be used to map elements from the vector space of fields back into itself, right? And so this is the group operation, and this is an element of the group operating on a vector in the vector space, right? Effectively changing its basis. And that's really important to understand. The members of the group are themselves tools that we use to change basis vectors in a vector space. But the members of the group themselves form a group under the operation under matrix multiplication, which, by the way, is the same as just taking 2 or 3 basis changes in a row, right? If one matrix changes a basis, let's say we operated on some kind of column vector, so we have our first basis change, and then we do a second one. Whoops, we do a second one, right? And we could do a third one, right? Now if we multiply these matrices together, that's going to be the same as one basis change instead of 3, right? Because we take the product of these 3 matrices, create one matrix, and then that operation is going to give you the same vector as this operation. So here we kind of use both the group operation property to create a single matrix, and then, that's our final tool, and we're going to use it to, say, change the basis of some vector. Now, what ends up happening, however, is this thing becomes interesting in its own right. We don't even really need to have a vector space all the time. This set of all matrices, is in itself interesting. It just so happens we came across the definition of a matrix through our desire to transform these column vectors. All right, so the column vector, this thing here, this vector space is often called the carrier space. The carrier space. This guy here is the transformation group. Transformation group. Right? And the transformation group will transform the bases of the carrier space. But the transformation group is in itself a group. This distinction is really important because it can lead to a lot of confusion down the road when you see how these things operate. You've got to remember that the group operation is matrix multiplication for these classical groups, and the members of the classical groups themselves, however, are defined by what they do on the carrier space. So when we go back here, and I look at all of these different groups, these different classical groups, each one of them does something special to the carrier space and is a group in its own right. That means all of these are groups of matrices, but say this group of matrices, the special orthogonal group, that will take a certain dimensional vector space and transform its bases in a certain predictable way. And all of those, and we'll define how that's done or what that way is soon. But the point is the collection of all the matrices that transform the bases of a certain carrier space in a certain way form their own group. But they're matrices, so they're necessarily a subgroup of one of these four, right? Because these four are all possible transformations of the basis vectors of those carrier spaces. These guys are not all possible transformations. They're very specific transformations, very specific class of transformations. And each one of them represents a different class of transformations. And but they all must form a group in their own right as matrices. And therefore they will all be subgroups of these guys. But they'll also all have the same property. They'll be a member of the classical groups, right? And also they will have an infinite number of elements, but they will still be a subset of the general linear groups. In fact, why don't we focus on one of them right now? In fact, there's a bunch that I did not write here. I did not write down SL N R, for example, or SL N C. Right, that's called the special linear group. Let's talk about the special linear group right now. So let's start with considering a vector space with over some F, and we'll give it 4 dimensions, right? And I'll get rid of E0 for the time being, just because I don't want to go up to n minus 1. I want to be able to look at this and say 4 dimensions. So we'll start with E1. So now I know that if I have a vector space, now this is going to go back a little bit to the what is a tensor material. So if you don't understand the tensors, this is a good time to catch up and go to those classes. But I'm presuming that you've covered most of what is a tensor. This is the early material, but you recall that you can form this completely antisymmetric basis. Given a vector space, you can create these exterior product spaces, right? And we can create the exterior product 1, exterior product 2, exterior product 3, and exterior product 4, right? Where these are all, and I guess exterior product 0, remember that guy. We can create these 4 exterior product spaces of different dimensions, dimension 0, dimension 1, 2, 3, and 4. Actually, that's not correct. I said that wrong, right? The dimensions of these things are actually, this one has dimension 1, right? The exterior product space, the 4th exterior product space has dimension 1. The 0th exterior product space, that also has dimension 1. The 1st and 3rd exterior product spaces, when the underlying vector space is 4-dimensional, has dimension 4. And the 2nd exterior product space, let's see if I can remember it, this has dimension 2 factorial, no, I'm sorry, not 2 factorial, 4 factorial divided by 4 minus 2 factorial, 4 minus 2 factorial, times 2 factorial, right? So that is going to be 4 factorial divided by 2 factorial, 2 factorial, 2 factorial, which is 4 times 3 divided by 2, which is 6, right? So this says dimension 6. Okay, so you may remember we have these 4 exterior product spaces. So if we look at the last one has dimension 1, and we know that the basis vector is written E1 wedge product E2 wedge product E3 wedge product E4. And we also know then that this exterior product space, we could consider a basis transformation of the underlying vector space, right? So we could say E I prime equals some matrix A, and I won't bother with the, well, I better bother. E, J, J, I, like that. And this matrix here is our transformation matrix. As such, it is a member of GL, one of these GLs, right? One of these GL groups. So, we studied it was always for real vector spaces, right? So we also know from our work, we learned that this transformation here will ultimately lead us to get the basis vectors E1 wedge, E2 wedge prime, E3 prime wedge, E4 prime. That would be the basis for the transformed version of this space. So this is the basis vector of the fourth exterior power when in the original basis, in this original basis, and this is the basis of the fourth exterior power after you change this basis to the prime basis using this matrix right here. But we know that this has to equal the determinant of A, which I'll draw that way, times the old basis, right? E2, E3, E4. And the determinant of A completely drives this whole thing. This, by the way, is called the volume element, as a reminder. This is the volume element of the fourth exterior power. So this guy here, this determinant, is the single number that makes a difference. And of course, if you have a one-dimensional vector space, which this is, remember, this is a single vector. And that's the one dimension of the one-dimensional vector space. So obviously, if you're gonna mess around with a change of basis in this vector space, it's got to come down to just a single number, right? That's all you have to play with. So this single number, this number is the determinant of the matrix transformation that's driven underlying vector space here. So now we can ask ourselves, all right, well, A could be any matrix. A could be any member of, and let's just consider the reals here. A could be any real matrix, right? That's invertible. So in principle, A could be any member of GL and R. Well, fine, that will definitely induce a change in this basis, and that will induce a change here where this number will become the new sort of factor of the basis system. But we could say, well, wait a minute. I'm only interested in changing the basis here in such a way that the volume element doesn't change. And that's tantamount to saying, I only want the members of GL of the general linear group where the determinant equals 1. And that is a subset. That is a subset of all the members of GLR, right? That's not all of them. That's just some of them. But what's interesting is that we know that the determinant of the product of two matrices equals the product of the determinants of two matrices. And therefore, and because of this, if I take any two matrices that have determinant 1 and I multiply them together, matrix multiply them together, and I take the determinant, I end up with another matrix that has the determinant of 1. So I've got another group, right? I've got another group. The inverse matrix of a matrix with determinant 1 will also have determinant of 1, right? So that's a subgroup of the general linear group, but it's actually called the special linear group NR. And so that's a perfect example of we pick a special transformation, a transformation that has determinant 1. We're motivated not because we arbitrarily want the determinant to be 1, but we're motivated by the fact that we don't want the volume element to change. We want it so that E primes equal E's, and that this basis vector, the basis vector that finds itself driving the construction of the fourth exterior power, we want that basis vector to be unchanged. And we know that transformation is driven by the determinant of whatever transformation we use for the underlying vector space. So that being our interest of what's called a volume-preserving transformation, well, the volume-preserving transformations have to be members of this group here, S, L, and R. Now, just for good measure, Gilmore points out that G, L, and C, this complex version, you can have the determinant of a matrix equaling the real number 1, or you could have the determinant of a matrix. Remember, there are complex numbers in the matrix. So in that sense, the determinant can be complex, but the modulus of the determinant has to be unity. So it's unimodular. So you can have two ways of getting what would be called a determinant to be 1. You can have a unimodular determinant, or you can have it actually equal 1. And there's two separate subgroups for that. But interestingly, for the quaternions, Gilmore points out that the non-commutativity of the quaternion field says that that's not true. It's not like the quaternions have 4 cases, right? They actually only have 1 case. And that's unimodular. So the quaternions have the special linear group for the quaternions, which I guess would be S, L, N, Q, is unimodular, which is different than having a determinant of strictly 1. But anyway, that's an example of how these classical groups are beat up. So this demand are composed, are structured. We start with a demand, and that demand in this case was that the volume form, right, doesn't change under the transformation. And then we go back here and we say, well, what subset of these general linear groups do that? In this case, it's the special linear group. But all of these are based on a different type of demand, and we have to go through that next time. We have to understand the different demands we have on the underlying transformation of the carrier space. And then we have to find the matrix group that executes that specific transformation. And then we cluster those together, we verify that it's a group, and then we call that and add it to our list of classical groups. And then the question is what is the relationship between these different groups? Okay, see you next time.